Moving on to lesson 5. This is also chapter 5 in our textbook. In this chapter, we're going to talk about steady-state electric currents. Right? As we progress, you should bear in mind the terminology steady electric current. Is it practical? What are the basic conditions and requirements to maintain a steady current? Okay, you have to think and ask yourselves that question. So in this chapter, I will cover the basic definition of current density, and we will talk about Ohm's law, which everybody here knows. Ohm's law is V equals IR. Right? Voltage is your current multiplied by the resistance. But we're going to look into that in more details. So somehow electromagnetics and electrical circuit will merge. And I want to convince you, basically everything being taught in electric circuit is actually covered by electromagnetics. And then we are going to talk about current laws, Kirchhoff's current law, okay? And then we're going to talk about boundary conditions, and then the method to calculate resistance, right? But anyway, how can you create current? Current, by definition, is you have moving charges, right? Think about it. If you have charge moving in space and time, then you have current, all right? So let's come to the blackboard. In the past, starting from high school, I bet each and every one of you already somehow touched current. So current, we like to use I. Capitalized I or non-capitalized I, doesn't matter, but I usually stands for current. And it has the unit of amps. Okay, so we have capitalized A to denote the unit for current. If we decompose amp into the basic units, it is actually coulomb divided by second. All right? So the definition of current is therefore physically how much charges you have flowing in certain time, okay? And therefore current adopts a unit of coulomb divided coulomb is the number of charge divided by the time duration, seconds, all right? So this is current in the unit of amps. But look at this picture. If you have current flowing, usually currents are actually vectors. Okay, but in the past, we understood currents as a scalar quantity. But now current can actually flow in different directions, right? So the better way to quantify current is we define some vector field, vector quantity called the current density. And then if that current density is making a dot product with some area, and that is equal to the current. All right? So basically, the current density is a vector, right? And it's nothing more than the current divided by the surface area. Surface area, okay? And therefore, its unit is amp per meter squared. All right? It's just the current density by definition is the amount of current per unit area. All right? So the unit is amp divided by meter squared. But in this PowerPoint, we're also going to introduce current density is actually having the charge density moving at certain velocity. So this rho is something we learned in the past. It's the current density, volume charge density, charge density and multiplied by the velocity. Okay? So you might want to check whether the charge density multiplied by the velocity gives you amps per meter squared. Okay, let's try to do that. So rho has a unit of charge divided by meter cubed. Okay, cubed, volume charge density. And this mu or u vector is velocity, so it's meter per second, right? So 1 meter is canceled out, but you know coulomb divided by second is just amp, okay? So this is equal to coulomb second and meter squared. So it is indeed amp per meter squared, right? So there are two ways to understand and appreciate current density. One is straightforward, the amount of current divided by your surface area. Another view to understand current density is you have a huge chunk of charges, and therefore you have charge densities, and these charges are moving at certain velocity, thus giving rise to current densities. Okay? Now, current densities can be divided into two types depending on how this current is formed, right? So the first one is called convection current, which is probably no longer in use, but in the past we used convection currents heavily. The second type is conduction current. This is something we use every day until this date, right? So by definition, convection current is something you have the motion of charged particles in vacuum. You don't see this nowadays very often, but if you are an audiophile, you listen to music, especially classical music, a lot of amplifiers like to use this so-called cathode ray tubes, 阴极射线管, right, to produce amplification. The working principle is you have two electrodes. Think of the capacitor, right? You have two conductors. And on one of it, you can apply a very high voltage. The other one is the ground. So you apply a very high voltage, you provide a huge electrical potential. So the positive side is having a very high positive potential, right? And thus, it would tend to attract the electrons out from the bottom electrode, right? So if you have very high positive potential, electrons can be sucked out of the conductor and swim to the positive side called the anode, right? Now, if you remember, electrons have negative charge, right? So as electrons are sucked out from the bottom electrode, it moves upwards. It is equivalent to a positive charge flowing in the reverse direction. Okay? So electrons flowing from the bottom to the up is equivalent to a positive charge moving from the anode to the cathode. So basically, the current flowing direction is from the top to the bottom. And usually for cathode ray tubes, you need to have a high degree of vacuum, all right? So you can enjoy convection current. So these are the charges really moving in vacuum. In vacuum means there's nothing to block the charges, okay? So this is convection current, but as I mentioned again, I mean, when I was little, the televisions we use are very thick because they are made of cathode ray tubes. But nowadays, you are all using the thin film liquid crystal type of monitors. So you don't really use cathode ray tubes anymore. And that leads us to the second type of current. It's called conduction current or drift current. All right, so conduction current, in comparison to convection current, this is a drift motion of charged particles, for example, electrons, and usually in conductors, in metals. Now, these blue big dots are the atoms within certain metal, and these small red circles are used to denote the electrons. Electrons are very light. Okay? They're very light. They're easy to move. So if you apply an external E field, the electrons tends to be moved by the external fields. But the dramatic difference between conduction current and convection current is here the electrons are provided by the metallic atoms. So you have lots and lots of atoms and a lot of electrons. Therefore, as the electrons move under the presence of external field, they tend to bump into each other. Like electrons can bump into another electron, or the atom, the nucleus of the atom tends to be bigger in terms of size, right? So electrons, they move, but they bump into each other or bump into the atoms. But overall, as they move, they bump. Overall, in general, you have a steady flow of electrons from the right to the left. Okay? So the apparent difference for conduction current is you have a drift of the overall motion of the charged particles to a certain direction, but as they move, they bump. Okay? Now, what is the effect of those bumping? Can you just try to understand it in a more physical way? You have a piece of conductor, you apply external field, you create the drift motion of electrons, and therefore you have current. But as the electrons move, they bump into each other or bump into the atomic lattice. Every time they bump, they lose certain energy. Right? And that energy, due to the bumping, is transferred into heat. Okay? And that is called resistance. Right? The higher the resistance means the electrons tend to bump more frequently in that given metal. Right? So the drift motion of free electrons undergoes frequent collisions or bumping. Right? And therefore you have resistance. Right? The next question we have to answer is, why is the drift motion flowing from the right to the left? Well, here we have assumed the externally applied E field direction is from the left to the right. This is, well, the direction, the starting point of the arrow means we have higher electric potential. or higher voltage. And in the direction of the arrow, you have a reduction in the voltage, right? So this is again conforming to the convection current. Electrons tends to be attracted by the positive potential, okay? So whenever you have positive potential, negative potential, you create the E field from the left to the right, but the electrons are attracted to the positive side of the potential, right? So electrons drift from the right to the left. But again, electrons carry negative charges, right? So equivalently, if you have a lot of negative charged particles flowing from the right to the left, it's equivalent to positive charged particles flowing in the direction of your applied field. Okay? So even in conduction current, the current density produced by the external applied field is parallel to your field. Okay? But in fact, in reality, it's the lighter weighted electrons that's drifting. All right? So, the drifting velocity of electrons is proportional to your applied field, but in the reversed direction. Okay? Okay, so I'm giving you some table for different materials. These are known. Aluminum, copper, silver, silicon, they all have different drift velocities. So these are tabled by this constant, all right? But what we really care about, these are too tedious. What we like to call materials, if they can have the ability to have conduction current, we like to use a simple parameter called conductivity. And starting from now on, for the entire semester, I'm going to use the Greek letter sigma to denote conductivity. All right? So basically, J, the current density, is indeed the charge density multiplied by the drift velocity. But if we understand this drift velocity is just this mobility constant multiplied by your external field. Okay? And then we can just say, okay, finally, once we have certain material, the externally applied field would be in the same direction as the current density created. And the magnitude is directly dependent on the conductivity of that given material, right? So if the conductivity for a certain conductor is very high, then it produces a huge current density, right? So carbon nanotube can actually give you huge currents as compared to common metals, all right? So these are just explanation of conductivity. And starting from now on, we can just use the sigma constant to describe different materials, right? Now, this is saying in electromagnetics, the way we understand about the current formation and the flow of current is somehow different as what we learned in the past in electric circuits, okay? In the language of electromagnetics, you have a piece of conductor. Once you apply certain potential difference, you create external field, and then you create the motion of drift electrons, and effectively, you create current density. Okay? So you have a piece of conductor, you have applied potential difference, you have therefore applied external field, and you create current density. And up to now, electromagnetics tells you, well, we can formulate and we can quantify the relationships of the resulting current density and your applied field intensity. And that is simply by knowing what type of a material you're using. So J equals sigma E. And that's it. That seems very unfamiliar, right? In the past, what we learned about was, in the circuit theory, was V equals IR. Voltage is equal to current multiplied by resistance. Okay? Now think about it. What's the difference between the two? Or eventually they mean the same thing. It's the same language, no, it's the same sentence, but spoken by two different languages. This is Mandarin Chinese, this is Taiwanese. Now think about it. What is the difference? And this is the page I really want to convince you. If you can master electromagnetics, basically you understand everything in circuit theory, ideally, if you really master electromagnetics. So let's try to prove these two are really the same sentence, but only pronounced in different languages. Okay? So V equals IR. What is V? V is the potential difference. And the potential difference is derived from the line integration of along the direction when you combat or against, you work against E field, right? So if you want to understand about the potential difference between these 2 points, this is 2, this is 1. If I want to understand the potential difference between points 2 and 1, all I have to do is perform integration. The line integration of my differential length and my field. Now you might be puzzled because in the definition of V, we focused on the fact that we need to add a negative sign, right? I spent a lot of time telling you V is the negative line integration of E dot dl. But how come in here I don't have the negative sign? Can anyone try to answer that by yourselves? This is the point where you have to understand how is this V defined in circuit theory. V equals IR. What does it mean? What is this V stand for? When you move in the direction of the current, you multiply by the device's resistance, you produce a voltage difference, potential difference. But when you have a positive V, what does it mean? Now go back and check your circuit theory textbook. Probably in the first chapter, up front, it will tell you we are working in the passive sign convention, which means if you have a positive V, it means you actually have a potential drop. Okay? So therefore, in order to match circuit theory using passive sign convention, a positive V means you have a voltage drop. Here, we removed the negative sign. Okay? To represent we actually have a drop in potential, a reduction in potential. Voltage drop. Okay? So as I move from point 1 to point 2 in the direction of the external field or in the direction of my current density, I expect to have potential drop. Okay? Therefore, here, I removed the negative sign. But now I know E is simply J divided by sigma, right? So this is telling you, well, in this simple case, I already know the surface area of my conductor, and that potential drop can be directly related to current multiplied by some constant. I know the length, right, from point 1 to point 2 being L. So everything is known. So the voltage drop is indeed equal to the current multiplied by another constant. So in this simple process, I have already derived the formula for calculating resistance, right? We can just call this as R as compared to the circuit theory. So basically, once you have a conductor, you know its length, you know its surface, you know its area, and you know its conductivity, you know its resistance. Okay? So I'm giving you a very simple, workout problem. You can try to calculate. So usually we use copper to make cables. So if the copper cable is 1 kilometer in length and it's in a circular geometry and the radius is 1 millimeter, try to calculate its resulting resistance if you know the sigma for copper is 5.8 times 10 to the 7th. Now try to do the calculation on your own. Okay? 1 kilometer of copper wire with that radius, probably around 5.5 ohms, extremely small.